Hello. Today, my team and I are here to present you about the deep learning project that we have worked on titled Trilingual Sign Language Translator. Our agenda for today's project discussion is team introduction, problem statement, deep learning architectures comparative study, multilingual sign language translator, results and discussion, and conclusion. These are the team members that we have worked on to contribute to this project. Our project is a twofold endeavor with the comparative study as a research part and trilingual sign language translator as an application part. We decided to work on this project as the research part without the application part is incomplete one and also the vice versa. In the comparative study, we wanted to strengthen the deep learning concepts that we have learned throughout the course. So to create the best performing model based on the defined metrics, we studied various machine learning and the deep learning architectures. Over 5% of the world population are suffering from the hearing loss and also the speaking loss. And also due to the lack of the professionals who are teaching this, it has become a challenging task to learn the sign languages. So we built a multiple sign language translator that can take communications in one sign language and translate them into the written text, as well as the other sign language hand gesture representations. We use the American Sign Language, German Sign Language, and the Indian Sign Language image datasets that consist of the 26 alphabets. Now, my friend Drumel will be here to talk to you about this research part.
So when it comes to the comparative study of deep learning architectures and when it comes to the research aspect, we need to be very sure that we use the algorithm in and out and we know the nitty-gritties as well as the basic assumptions of every algorithm. So for our project, we'll be implementing 5 different architectures starting from classic sequential neural network and going to the most influential model, that is AlexNet. So first we implemented a classic sequential neural network model with a lot of layers such as a convolution and dropout, then max pooling and a flattened layer as well. So in total we had 16,000 total parameters and then we found an accuracy of around like 98%. And the second model which we implemented was convolutional neural network model, as it is one of the most classified model which needs to be used for a high dimensional image without using any information in that. So here also we used 2 dense layers, 2 max pooling layers, and 3 convolutional neural networks. And here in total we had like 4,59,000 parameters with us. This is the epoch visualization for both training accuracy, test accuracy, and loss as well. So we can clearly see that the model a bit overfits when the number of epochs increases. For our case, we have used the epoch number to be 100. The third model which we implemented was VGG16 model, which is believed to be like they can classify 1,000 images on 1,000 different sets with an accuracy of 92%. So here we had 15 lakh parameters and we used 3 layers such as VGG, that is a functional layer, dense layer, and the flattened layer. And this is the visualization of the epoch, and we clearly see that the model overfits from the first aspect itself, like from the first 10th epoch. And the fourth model which we implemented was the DenseNet model. Why DenseNet model? DenseNet it is used to improve the object detection as we need to identify the hand gestures related to that. And this block diagram shows us how we believe to be our architecture is. And so starting with the ReLU layer and going to the transaction layer, the transition layer. Like we got a very less accuracy for the DenseNet model. So we wanted to know how much each and every gesture was able to represent themselves. So we used precision recall, F1 score, and support for each and every label starting from 0 to 28 label, that is 29 labels in total. And we found out each and every precision recall value for each and every label. The last model is AlexNet model. AlexNet model has its own superficial ideas where it was one of the most influential paper when it comes to the extension of convolutional neural network models. So we had then input image of 227 by 227 into 3 channels, and then we classified it into 13 by 13 by 256, and later we got an output of like 4096. Here we found the change in cost as well as the change in accuracy, and we found that the accuracy was pretty wavering when the number of epochs increased, as it was very time consuming and we used GPU for this model. So we kept our epochs to be the number of 25, and we found that this was the change of cost as well as the change in accuracy. And we used an Excel to find the accuracy pattern for different experiments. We could clearly see that the DenseNet was one of the models which did not perform very well as compared to other models. And after DenseNet came the neural network model, that is the sequential API which we use, and the best model which we have, like in our case, was convolutional neural network model. The next case would be explained by Shivangi.
For the application part, we decided to build the multilingual sign language translator. We decided to work on this as we thought this was a good opportunity to work on a project which catered to the minority part of a society. The best performing model during our research was a convolutional neural network model, and we decided to use that with some minor modifications for this application part. In our model, we took data sets for different sign languages like the American Sign Language, German Sign Language, and the Indian Sign Language for alphabets A to Z. We pre-processed the data by normalizing it and doing label encoding. For training part of the data, we used activation functions like ReLU and Softmax and Adam as the optimizer. We also built an image data generator who worked on image features like center, normalization, brightness, and the zoom. Once we fit the model, we received our results and got a test accuracy of 96.2% as well as a test loss of 14.9%. We predicted the images. The way it worked was that once the language was predicted for a particular image, for example, the prediction was F letter of the American Sign Language. It also gave us the F letter for the Indian Sign Language and the German Sign Language, making it easy as a translator for people who have disabilities to understand. In conclusion, we were successful in this twofold endeavor as we were able to do our research as well as build a system and apply that research towards a translator. There are still some gaps that may be something that we work on in the future as it's really static and it just creates alphabets from A to Z. But it's definitely that will be something that we take up and work on as we enhance and optimize it. Thank you.